Data-intensive application, reliable, scalable, maintainable applications. Many applications today are data-intensive as opposed to compute-intensive. Raw CPU power is rarely a limiting factor for these applications. Bigger problems are usually the amount of data, the complexity of data, and the speed at which it is changing. A data-intensive application is typically built from standard building blocks that provide commonly needed functionality. For example, many applications need to store data so that they or another application can find it again later. Remember the result of an expensive operation to speed up reads, caches, allow users to search data by keyword or filter it in various ways, search indexes, send a message to another process to be handled asynchronously, stream processing, periodically crunch a large amount of accumulated data, batch processing. This book is a journey through both the principles and the practicalities of data systems and how you can use them to build data-intensive applications. We will explore what different tools have in common, what distinguishes them, and how they achieve their characteristics. In this chapter, we will start by exploring the fundamentals of what we are trying to achieve: reliable, scalable, and maintainable data systems. We'll clarify what those things means, outline some ways of thinking about them, and go over the basics that we will need for later chapters. In the following chapters, we will continue layer by layer, looking at different design decisions that need to be considered when working on a data-intensive applications. So basically, the common issue is data, not really the raw computer power anymore. So it's how you organize those data in the system. Also, it's an application of the right decision or making the right tool or data application decision that's specialized, and how you combine those tools to achieve your goal. Kind of like the recurring theme that happen with computer science subjects is that you need to use the right tool at the right case. Thinking about data systems, we typically think of databases, queues, caches, etc. as being very different categories of tools. Although a database and a message queue have some superficial similarity. Both store data for some time, they have very different access patterns, which means different performance characteristics, and thus very different implementations. So why should we lump them all together under an umbrella term like data systems? First, many new tools for data storage and processing have emerged in recent years. They are optimized for a variety of different use cases, and they no longer neatly fit into traditional categories. For example, there are data stores that are also used as message queues, like Redis, and there are message queues with database like durability guarantees, like APIC, Kafka. The boundaries between the categories are becoming blurred. So because these tools kind of become blended and more sophisticated, because they are able to handle those edge cases that they previously were not able to handle. Secondly, increasingly many applications now have such demanding or wide-ranging requirements that a single tool can no longer meet all of its data processing and storage needs. Instead, the work is broken down into tasks that can be performed efficiently on a single tool, and those different tools are stitched together using application code. For example, if you have an application managed caching layer using Memcache or similar, or a full text search server such as Elasticsearch or Solar, separate from your main database, It is normally the application's code's responsibility to keep those caches and indexes in sync with main database. So the application developer also have to worry about this data model. Therefore, they also need to understand this in how to interact with these things. Figure 1.1 gives a glimpse of what this may look like. We will go into the detail in later chapters. So you can see we have a client uh, interacting with an API with an in-memory cache, and it will read requests. First, check if data is cache. If not, it will invalidate the cache or update the cache, and then the application code also must handle that, and then apply updates to search index. So this full text index does the Elasticsearch provide, that allows you to send text need to be integrated, needs to be updated with the primary database. So if it cache misses, it writes to the primary database, and it also has a message queue that handle asynchronous tasks. As you can see, these are all interconnected. Figure 1.1, one possible architecture for a data system that combines several components. When you combine several tools in order to provide a service, the service interface or application programming interface API usually hides those implementation details from clients. Now you have essentially created a new special purpose data system from smaller general purpose components. So this is what happened without you understanding, or even if you are aware, this is what happens. Even though this is actually how people create their thesis, though they are not aware that they are combining or making use of these different data models, though they intuitively are able to create or to connect those systems, but internally this is actually what happened. The application code are now making those boundaries, or we shall say workarounds, to make those system works. So it's not just saying that data model, only data model now, or just one tool, or this a tool could be complicated, and it has a different characteristics on its own, kind of like a human or a person. You can't really define a person as good or bad because it's different on who you ask, and in different situations, right? Your composite data system may provide certain guarantees, i.e., that the cache will be correctly invalidated or updated on writes, so that outside clients see consistent results. You are now not only application developer but also a data system designer. If you are designing a data system or service, a lot of tricky questions arise. How do you ensure that the data remains correct and complete, even when things go wrong internally? How do you provide consistently good performance to clients, even when parts of your system are degraded? How do you scale to handle an increase in load? What does a good API for the service look like? There are many factors that may influence the design of a data system, including the skills and experience of the people involved. Legacy system dependencies, the time scale for delivery, your organization's tolerance of different kinds of risk, regulatory constraints, etc. Those factors depend very much on the situation. In this book, we focus on three concerns that are important in most software systems. Just a moment. First, reliability. The system should continue to work correctly, performing the correct function at desired level of performance, even in the face of adversity. Hardware or software faults, and even human error. See reliability on page 6. Scalability. As the system grows in data volume, traffic volume, or complexity, there should be reasonable ways of dealing with that growth. See scalability on page 10. Maintainability over time. Many different people will work on the system, engineering and operations, both maintaining current behavior and adapting the system to new use cases. And they should all be able to work on it productively. So these are the key metrics to simplify our understanding on how do we actually create a big system or complicated system that withstand many concurrent customers and stand the test of time. So we'll start with reliability. We can understand reliability as meaning roughly continuing to work correctly even when things go wrong. The things that can go wrong are called faults, and the system that anticipate faults and can cope with them are called fault tolerant or resilient. The former term is slightly misleading. It suggests that we could make system tolerant of every possible kind of fault, which is reality is not feasible because anything can happen. So there's actually in statistics, the things we know today are just 99% correct. There's always 1% chance that it could be incorrect. So this is what it is pertaining about. So it means that there could be unpredictable behavior that could change how we view the system. Kind of like a software as well. It works until it doesn't because some bug persists in it that the environment do not that for a long time until a change in environment causes them to cause a bug. Note that a fault is not the same as failure. A fault is usually defined as one component of the system deviating from its spec, whereas a failure is when the system as a whole stops providing the required service to the user. It is impossible to reduce the probability of a fault to zero. Therefore, it is usually best to design fault tolerance mechanisms that prevent faults from causing failures. Counterintuitively, in such fault-tolerant systems, it can make sense to increase the rate of faults by triggering them deliberately. For example, by randomly killing individual processes without warning, many critical bugs are actually due to poor error handling. Although we generally prefer tolerating faults over preventing faults, there are cases where prevention is better than cure, i.e., because no cure exists. This is the case with security matters. For example, if an attacker has compromised a system and gained access to sensitive data, that event cannot be undone. However, this book mostly deals with the kinds of faults that can be cured as described in the following sections. Hardware faults. When we think of causes of system failure, hardware faults quickly come to mind. Hard disk crash, RAM becomes faulty, the power grid has a blackout, someone unplugs the wrong network cable. Anyone who has worked with large data centers can tell you that these things happen all the time when you have a lot of machines. Therefore, it is expected for you to prepare for this. Just like in your instance, for example, you deploy in cloud, you should have a backup instance for your application service, because this happens all the time, even in AWS, because they are optimized for flexibility rather than this single failure. So hard disks are reported as having a mean time to failure MTTF of about 10 to 50 years. 5. Thus, on a storage cluster with 10,000 disks, we should expect on average 1 disk to die per day. Our first response is usually to add redundancy to the individual hardware components in order to reduce the failure rate of the system. Disk may be set up in a RAID configuration. Servers may have dual power supplies and hot swappable CPUs. So hot swappable meaning you can take out the CPU even if the PC is turned on. And a RAID configuration, it's a technique particularly in disk that allows you to have kind of like a replicate or additional disk on the server to be there to be a fallback in case one that disk got broken. And data centers may have batteries and diesel generators for backup power. When one component dies, the redundant component can take its place while the broken component is replaced. This approach cannot completely prevent hardware problems from causing failures, but it is well understood and can often keep a machine running uninterrupted for years. Until recently, redundancy of hardware components was sufficient for most applications since it makes total failure a single machine fairly rare. As long as you can restore a backup onto a new machine fairly quickly, the downtime in case of failure is not catastrophic in most applications. Thus, the multi-machine redundancy was only required by a small number of applications for which high availability was absolutely essential. However, as data volumes and applications computing demands have increased, more applications have begun using large numbers of machines, which proportionally increases the rate of hardware faults. Moreover, in some cloud platforms such as Amazon Web Services, it is fairly common for virtual machine instances to become unavailable without warning. So as you increase machine, of course you will increase fault because each machine has a corresponding percentage of fault in it. It's just the nature of complexity. The more hardware you have, the more complex it is. So that's called distributed systems complexity. The more it is, the more it is complex to track whatever is going on in the system. And later we will discuss how actually software is kind of act like that because it's hard to interpolate, or it's hard to troubleshoot if the issue if you don't have a deep understanding of the system because they are all interconnected. So to become unavailable without warning, as the platforms are designed to prioritize flexibility and elasticity over single machine reliability. Hence, there is a move towards systems that can tolerate the loss of entire machines by using software fault tolerance techniques in preference or in addition to hardware redundancy. Such systems also have operational advantages. A single server system requires planned downtime. If you need to reboot the machine to apply operating system security patches, for example, whereas a system that can tolerate machine failure can be patched one node at a time without the downtime of the entire system, a rolling upgrade. So to move beyond the hardware, there's actually software tolerance, fault tolerance techniques, or in which you use software to make your system fault tolerant or to increase your anti-fragility to fault. So it has an advantage because instead of waiting for an entire machine to actually do a downtime if you only have one machine, this software fault tolerant is that since you're handling it through software, therefore it is more flexible, you can patch one at a time or node at a time. So node or byte at a time or memory at a time, etc. Basically you're updating something in the disk that will then transfer to your memory and be executed by your processor later. Software errors. Another class of fault is systemic error within the system, such as faults. Such faults are harder to anticipate, and because they are correlated across nodes, they tend to cause many more system failures than uncorrelated hardware faults. So like what I mentioned, software is interconnected. They are harder to anticipate and troubleshoot, unlike hardware, which has uncorrelated hardware faults. So example include software bug that causes every instance of an application server to crash, when given a particular bad input. For example, consider the leap second on June 30, 2012 that caused many applications to hang simultaneously due to a bug in the Linux kernel. Second example, a runaway process that uses some shared resource, CPU time, memory, disk space, or network bandwidth. So it's kind of like the what the OS have solved for us, right? It prevents some process to take over our hardware resources, but sometimes a software bug could increase this risk that already abstracted to us by the OS. So imagine we need to be an OS developer as well. So another thing is that an instance on the cloud server causes it to crash because of a given input on its database. For example, a leap second that caused many applications hang simultaneously due to a bug in Linux kernel, which has been caused by the bad input of the user on Linux kernel that allows it to be cascaded to all application instance around the world. A service that the system depends on that slows down, becomes unresponsive, or starts returning corrupted responses. So if it slows down, of course it will not be able to serve the user. More importantly, if it return corrupted responses, and it will have a ripple effect because it could cause a delay to the customer's business, a security vulnerability that cause legal risk, etc. Cascading failures where a small fault in one component triggers a fault in another component, which in turn triggers further faults. The bugs that causes these kinds of software faults often lie dormant for a long time until they are triggered by an unusual set of circumstances. In those circumstances, it is revealed that the software is making some kind of assumption about its environment, and while that assumption is usually true, it eventually stops being true for some reason. There is no quick solution to the problem of systemic faults in software. Lot of small things can help. Also, with respect or with relates to this lot of small thing, this is very important in software, which you can apply in your daily life or in any field that you may encounter in the future, is that they think in small things, like carefully thinking about assumptions and interactions in system, like thorough testing, process isolation. So you isolate the process in an operating system. That's what you do. You layer the systems in network. That's how they did that. It's actually just a software, the network. Testing, each function is being tested to make sure that it's returning a correct value, allowing process to crash and restart, measuring, monitoring, and analyzing system behavior in production, tracking logs, everything that you could track to make sure using new tools to better understand the system, such as an API that will allows you to track different things throughout your system. And also, this is actually how you become good at code as well. You need to code even one small thing every day to not lose this momentum, because any bigger things start with a small thing, right? If a system is expected to provide some guarantee, for example, in message queue, that number of incoming messages equal the numbers of outgoing messages. It can constantly check itself while it's running and raise an alert if a discrepancy is found.